Dear students, today we will start or begin a new chapter, namely Laplace transform. And this is the first class, and this chapter will be covered or will be completed through a number of lectures. And this is the first one. And in this class, we will cover the following topics. Number one, a brief introduction about Laplace transform, then definition of Laplace transform, after that, conditions of Laplace transform, and finally, Laplace transform of some elementary functions. So, here are these topics, and now let us start. First, introduction. So, Laplace transform actually offers a direct method to solve a linear and ordinary differential, linear ordinary or partial differential equation. That is, these Laplace transform are very beneficial in case of solving of linear ordinary differential equation as well as partial differential equations. And what we do in that cases, actually in that case, this method is used to produce or to produce into a subsidiary equation from a given uh, uh, given linear ordinary differential equation or partial differential equation. That means whenever you will apply Laplace transformation on linear ordinary or partial differential equations, then it will give you some subsidiary equation, and those are basically algebraic equation, and then they can be recast into a convenient form, and the inverse Laplace transformation of the recast algebraic equation gives the solution of differential equation. So whenever you apply Laplace transform to for a linear ordinary or partial differential equation, then it will provide you a number of equations, algebraic equation. Those are called subsidiary equation, and after that you can recast this subsidiary equation to the given problem on given differential equations. And after that, the inverse Laplace transformation of the recast algebraic equation give you the solution of the differential equation that it have provided. And these will be very clear when we will solve some differential equations. So, and this Laplace transformation or this transformation is very powerful technique, and promising technique to analyze time invariant systems such as elliptic circuits, harmonic oscillators, optical devices, solar cells, etc. So for those cases, we can use you can use Laplace transform to solve those problems or analyze those time invariant systems. And this method, furthermore, this method is effective for boundary value problems of differential equation in physics, not only in physics but also in mathematics or any other sections of engineering. That means this method is very helpful and fruitful to discuss or to analyze different boundary value problems in physics as well as mathematics or in engineering. So now come to the next point, that is the definition of Laplace transform. So let us consider that you have given a function fx, and the Laplace transform of this function is given by fp. Okay, fp that is equal to L square bracket fx, and this is the Laplace transformation of the function fx, and fp, that means this will provide a new function fp. Okay, and the function should be defined for all values of x. So let us consider we have given a function fx which is defined for all values of x. Then the Laplace transformation of this function fx is denoted by fp, that is equal to L, that means Laplace transform, then square bracket of fx, and it is mathematically defined as fp, that is equal to Lfx, that is equal to 0 to infinity e to the power minus px fx dx. This is the mathematical definition or definition of Laplace transformation. You should remember this definition. So fp, that is L of fx, that is equal to 0 to infinity e to the minus px fx dx. And this provided the integral, this integral should exist. Okay, unless and until this integral exists, you cannot able to find out the Laplace transformation of the function fx. And you see, this p is a parameter which may be real or complex. This parameter p may be real or complex number, and it is called a Laplace transform parameter. This in this definition, p is called the Laplace transform parameter, and this can be, it can be both real or complex. Now let us see this definition. From this definition, it is very clear that the Laplace transformation of the function fx, that is given here, and this is nothing but a function of p. And since this is the Laplace transformation of fx is a function of p, then it can be written, that is the Laplace transform can also be denoted by small p, that is this is a function of p. So the Laplace transformation of the function of x will provide you another function, that is fp, and then in that case Laplace transformation can also be denoted by fp. Therefore, we can have now we can have Laplace transformation fx, that is fp, that is 0 to infinity to minus px fx dx. And now the operator L that transforms the function fx into a function fp is called the Laplace transform operator. And therefore, this is the Laplace transform operator, and this operator actually transforms the function fx into another function fp. So now the conditions of Laplace transformation, here we have summarized conditions of Laplace transforms, and these are: number one is here the integral part, that is this part 0 to infinity e to the power minus px fx dx. These should exist, and if that means if 0 to a e to the minus px fx dx can actually be evaluated and it exists as it tends to infinity, then and the Laplace transformation of the function fx can be carried out. So this is the first condition. That means e to the minus integration 0 to infinity e to the minus px fx dx should exist. Then number two is the Laplace transformation of fx exists if the integral of equation 1, that means this is the equation 1, 0 to infinity e to the minus px fx dx, this converges for some value of p. So this value should be converged for some value of p. So this is the second condition, and the third condition is here: the function fx should be continuous, or at least it should be piecewise continuous. Okay, so these are the three conditions of Laplace transforms. Number one is the integral part, that is 0 to infinity e to the minus px fx should exist. Number two, fx, the Laplace transformation of fx exists if the integral converges for some value of p. And number three is the function fx should be continuous, or at least piecewise continuous. So now come to the next topic, that is Laplace transform of some elementary functions. So in this section we will calculate the Laplace transform of some elementary functions. Number one is Laplace transformation of 1, and that is equal to 1 by p, providing p greater than 0. So we are here to prove this, that Laplace transformation of 1 is equal to 1 by p. So proof is here. The Laplace transform, you know that if you have a given function fx and its Laplace transformation can be defined as, or can be given by f function of fx, that is 0 to infinity e to the minus px fx dx. Okay, this is the definition of the Laplace transformation of the function fx. And in the present case, here fx, that means fx is nothing but a 1. So the Laplace transformation according to this definition is if Fx means that is in this case fx is equal to 1, that is constant. And in this case, so therefore according to the definition, the Laplace transformation of 1, that is f of 1, this should be square bracket, f of 1, that is equal to 0 to infinity to the minus px dx. Because in this case, your this fx is nothing but 1, so e to the minus px then into 1 into dx. So now we are here to compute the integral of this function in the limits 0 to infinity. So you know that integration of e to the minus px is equal to minus px by p, or e to the power minus px by minus p. Okay, 0 to infinity. So if you use the limit infinity, then this will give you 0 null result. After that, for the lower limit, another negative sign will come. Then these two negative sign will provide you a positive sign. After that, if you use 0, then it should provide 1 by p, and providing in this case p should be greater than 0. Therefore, function Fourier transform of 1, that is equal to 1 by p. Okay, that is 1 by p, and you can also rewrite this L of L using this bracket instead of square bracket. You can also write this in this way. There will be no problem. And in this way, if you wish to find out the Laplace transform of any constant c, then this will give you a result c by p. Okay, if of 1 is equal to 1 by p, then you can write this since c is a constant, so you can write this as L c, that means L Laplace transform c into 1, that will provide c by p. Now another problem is there. Laplace transform of x to the power n, that is equal to n factorial by p to the n plus 1, and that is equal to gamma n plus 1 by p to the n plus 1, where n is equal to 0, 1, 2, 3. This should be proved here in this problem. So the given function, let the given function is fx, that is equal to x to the power n. Then from the definition, the Laplace transform of the function, you know, if that fx is equal to that can be denoted by in this way, L of fx, that is equal to 0 to infinity e to the minus px, then fx dx. In the present case, fx is x to the power n. Then Laplace transform of x to the power n, that is equal to 0 to infinity, then e to the minus px, then x to the power n dx. Now just substitute this px as r. So from here you can write x is equal to r by p, and therefore from this relation p dx is equal to dr, or dx is equal to dr by p. Now just substitute the value of this px as r and dx as dr by dp in this relation, in this expression. That is done here. So L Laplace transform x to the power n, that is equal to 0 to infinity, then e to the power, since px is equal to r, so that is e to the minus r. After that, x to the power n means your here is that r by p to the power n, then dx, that means dr by p. So that is equal to from here r to the power n and p to the power n. So p to the power n is here 1 by p to the power n, and here is 1 by p, so that will give you 1 by p to the power n plus 1, then 0 to infinity e to the power r, after that r to the power n dr. Okay, so that is equal to what is that is equal to gamma n plus 1 by p to the n plus 1, because you know the definition of gamma function, that is 0 to e to infinity e to the minus x, then x to the power n minus 1 dx, that is equal to factor gamma n. So e to the minus x, then x to the power n minus 1 dx. In this case, okay, it is e to the minus r, and this is actually n plus 1 minus n. So this will give you gamma n plus 1 by e to the n plus 1, and you know that gamma n plus 1 is n factorial by p plus n e to the power n plus 1 by p to the n plus 1. So the Laplace transform of the function x to the power n, that is equal to gamma n plus 1 by p to the power n plus 1, that is equal to n factorial by p to the power n plus 1. Some other Laplace transforms let here, see here. First Laplace transform of x is calculated here using this relation. So in this case, n is equal to 1. So from this relation you have Lx, that is equal to Laplace transform of x, that is equal to 1 factorial by p to the 1 plus 1, that means 1 by p square. And here is the second one, x Laplace transformation transform of x to the minus half. So in this case, n is equal to minus half. So the Laplace transform is here 0 to infinity p to the minus px x to the power minus half dx. We can write this in this way. So in this way you can write this, or you can directly use this relation that is equal to gamma and n is in this case minus half, then plus 1 by p to the power minus half plus 1. So that is here on Laplace transform of x to the power minus half, that is equal to, this will give you gamma half and this will give you e to the power half. So that is equal to, you know that gamma half is equal to root pi, square root pi, and here is p to the power half, that will give you square root pi by p. Here is written here gamma half is equal to root pi, square root pi. Then x to the power half, in this case n is equal to half, so use the just use this relation, gamma half plus 1 by p to the half plus 1, that is equal to gamma 3 by 2 by p to the 3 by 2, and you can write this as half plus 1 by p to the power 3 by 2, and you know that gamma n plus 1, that is equal to n gamma n. So in this case n is half, so n gamma n means half gamma half by p to the 3 by 2, that is equal to half, you know gamma half is equal to square pi by p to the 3 by 2, or L or Laplace transform of x to the power half is equal to square root pi by 2 to the power 2 into e to the 3 by 2. After that, now we are here to compute the value of Laplace transformation of e to the power ax, and it is equal to 1 by p minus a. We have to prove this, and to prove this, let us consider the given function fx is equal to the power ax, and then the Laplace transformation of this function e to the power ax is equal to from the definition 0 to infinity e to the minus px, and then this e to the power ax dx, that is equal to 0 to infinity e to the power from this minus is here common, then p minus ax dx, that is equal to the minus p minus a. So the integration of this function is e to the power minus px by minus p minus a, 0 to infinity. So now if we use the limit infinity, then this will go into 0, and for the lower limit this minus and another minus will appear due to the lower limit, so this will get a positive sign, and then 0, if you use that 0, then this will go into 1, and this will give you p minus a. So finally we obtain Laplace transform of e to the power ax is equal to 1 by p minus a. Now just use the value a as 1 in this expression. That is, if a is equal to 1, then what we will have? Then we will have Laplace transform of e to the power x, that is equal to 1 by p, and a is 1 in this case, 1 by p minus 2. So the Laplace transform of e to the power x is equal to 1 by p minus 1. After that, Laplace transform of sin ax, that is equal to a by p square z square. So in this case, the given function fx is equal to sin ax. So let us do the Laplace transformation or calculate the Laplace transformation of this sin ax. So that is here Laplace transform of sin ax, that is equal to 0 to infinity, then e to the minus px, then the function is here sin ax dx. And now that I1 is equal to this integral, that is the e to the power minus px sin x dx. Just write this part, integration e to the power minus px sin ax dx, that is equal to I. So the value of I1 is here, so I1 is equal to here. So you should compute, or you should use the integration by the method integration by parts. This method should be employed in this case. So in that case, your e to the minus px is first taken as constant, then integrate this sin ax dx, that will give you minus cos ax by a, then minus, then differentiate this term, that will give you minus p to the minus px. After that, integrate this sin x, that is minus cos x by a, then dx. So I1 is equal to here e to the power minus px the negative sign, then cos x, then minus from here p by a is here, e to the minus px cos x dx with negative sign. This is equation number 3. Now we have to compute this integral, compute the value of this integral. So let us consider that this part is equal to I2. So this should carry out the same methodology as used in this case, that is first e to the minus px is here, then integrate this cos x, that will provide you sine, that will give you sine ax by a. After that minus, then differentiate this minus p, then e to the minus px, then integrate this cos x, that will sine ax by a, that a is here, then dx. So I2 is equal to e to the minus px sine ax by a, then this negative sign give positive sign, p by positive sign, p by a, e to the minus px sine ax, sine dx, ax dx. So that is equal to see here, this e to the minus px sine ax dx, that was taken as I1. So this is actually I1, this part is actually I1. So I2 is equal to e to the minus px sine ax by a, then plus p by a, then I1. It is from equation number 1, you know that this part is I1. So then from this relation you can write I1 is equal to, so therefore from this relation, from this equation number 2, from this relation you can write I1 that is equal to e to the minus px with a negative sign, or equation number 3, it is better to write equation from equation number 3. So equation from equation number 3, I1 is equal to e to the minus px by a, then cos x minus p by a square, because you have to, this term is actually this, so minus p by a should be multiplied with both these terms. So first term will provide you minus p by a square e to the minus px sin x, then minus p square by a square I1. So now just take this term in the left hand side, so that will provide you I1 into 1 plus p square by, here is I1, so I1 is common, so 1 plus this p square by a square, that is equal to minus, it is minus px by a, then cos x minus p by a square into the minus px sin ax. So from here just simplify I1 a square plus p square by a square, that is equal to e to the minus px by a square. It take this as common term, e to the minus px by a square. Then here the left term will be a cos ax, and from here plus p sin ax, the negative sign is taken here. So a square will cancel out each other. So I1 is equal to minus e to the minus px by a square plus p square a cos x plus p sin x. So the integration, that is the limit, was 0 to infinity of this. So that is here 0 to infinity to the minus px sin x sin ax dx, that is equal to you should use the limit here. So minus e to the minus px by a square plus p square, then a cos x plus p sin x 0 to infinity. Just use the limit. Here in this case, and that is for infinity, this will produce 0 null result, and for the lower limit another negative sign will appear here, so negative positive sign, and after that if you use the value 0, this will provide you 0 null result, and from here 1 by a square plus p square, and from here a into 1, that means a by a square plus b square. So in the denominator there should be a square plus b square during that is here. So 0 to infinity to the minus p square sin ax dx, that is a by a square plus p square. Therefore the Laplace transform of sin ax is equal to a by a square plus p square. And now if you use a is equal to 1, that means Laplace transform of sin x, that is equal to, in this case a is equal to 1, so I use the value a is equal to 1 in this expression, that is then it will give you Laplace transform of sin x, that is equal to 1 by p square plus 1, p square plus 1. Here is alternative method, and this method is very easier compared to this method. So you can use any one of these methods. You can apply. So here is that Laplace transform from sin x. So you can write sin x as e to the iax minus e to the minus iax by 2i. Sin x can be written in this way, in this fashion. You know this formula. and then 1 by 2y is there. So you can write these two terms, since it is algebraic sum of two functions. So the Laplace transform of that two functions can be written in this way. So this is first you write 1 by 2y, then Laplace transform of e to the ax minus e to the minus ax, and you can write this as 1 by 2y is there, then Laplace transform of this first term e to the ix minus Laplace transform of the second term, that is e to the minus iax, and you already have calculated the value of Laplace transform of e to the ax. So what was that? E to the Laplace transform of e to the ax was 1 by p minus a, 1 by p minus a. So in our present case, for the first transform, Laplace transform, a is here plus ia. So the Laplace transform of this e to the ix should be 1 by p minus ia. So you have the knowledge of Laplace transform of e to the x, that was 1 by p minus a. So here is ia instead of a. So we write here p minus ia, and then minus is there from here 1 by p minus of minus ia, that will give you p plus ia. Just you have to just simplify this. So Laplace transform of sine x, that is equal to 1 by 2i is here, and from here first p plus ia, then minus p plus ia. So p will cancel each other, and from here 2ia will be there. So 1 by 2i into 2ia by p square plus a square, that is equal to 2 by 2a will cancel each other. So a by p square plus a square. So Laplace transform of sine x is equal to a by p square plus a square, and if you write a as 1, then Laplace transform of sine x, that will be here a is equal to 1, so 1 by p square plus 1. So this is there. So Laplace transform of sine x is equal to 1 by p square plus 1. Now Laplace transform of cos ax. So here is that Laplace transform of cos ax is equal to p by a square plus p square. So now we are here to compute it. So Laplace transform of cos x, that is Laplace transform of e to the iax plus e to the minus ix by 2. You know this formula, and this cos ax can be written in this fashion. So that is equal to half Laplace transform of e to the iax plus Laplace transform of e to the minus iax. So that is equal to half. This half is here, and then this will give you 1 by p minus ia, and this will provide you 1 by p plus ia, because you know e to the power Laplace transform of e to the power ax is equal to 1 by p minus a. So that is here. After doing that, we obtain this, that is equal to this half is here, and from here p plus ia, and then plus p minus ia, and this plus ia will cancel each other. From here you will have 2p. So half, then 2p by p square plus a square, that is equal to p by p square plus a square. So Laplace transform of cos ax is equal to p by p square plus a square. So from here, if you write a is equal to 1, then Laplace transform of cos x, that will be p by p square plus 1. So it can be computed from this. Now Laplace transform of sine hyperbolic ax. So Laplace transform of sine hyperbolic ax, that is L of, you can write sine hyperbolic ax as e to the power x minus e to the minus x by 2. This is this you can write sine hyperbolic ax in this fashion, in this way. This is the formula to express sine hyperbolic ax. So L of e to the power x minus e to the minus x by 2. So that is equal to half. This half is here, L of e to the x minus L of e to the minus ax. Now just use the formula, that is Laplace transform of e to the x, that was 1 by p minus a. So in this case, so that will give you half, then 1 by p minus a, and from the second term that will give you 1 by p plus a. That is equal to this half is here, and from here p plus a, then minus p plus a. So 2a will be there. So half 2a by p square minus a square from here. So that is equal to a by p square minus a square, and then therefore we obtain Laplace transform of Sine hyperbolic ax is equal to a by p square minus a square. Now you use a is equal to 1 in this expression, that will provide you Laplace transform of sine hyperbolic x, that is equal to 1 by p square minus a square. So this can also be calculated from using this relation. And here is another one, that is Laplace transform of cos hyperbolic ax. Cos hyperbolic ax. So you can also write cos hyperbolic ax in this way, cos hyperbolic ax is equal to x plus e to the minus ax by 2. That is half L of e to the x plus e to the minus x, and that is equal to half is here, then L of e to the x plus L of e to the minus x, that is equal to half 1 by, from here, p minus a, and from here 1 by plus 1 by p plus a, that is equal to half from here, from p plus a, then plus p minus a will cancel each other, so 2p will be there. So half 2p by p square minus a square. So cos hyperbolic ax, that is equal to p by p square minus a square. And from here, from this relation, you can calculate Laplace transform of cos hyperbolic x. Cos hyperbolic x, that is equal to, that means in this case, a is equal to 1. So from this relation, cos hyperbolic Laplace transform of cos hyperbolic x hx, that is equal to cos hyperbolic x is equal to p by p square minus 1. So this is all about the Laplace transform of fundamental or elementary functions, and these Laplace transforms of different elementary functions will be used to solve different problems, and these are very important. So you have to the knowledge, you have the knowledge, you have the knowledge, you have the knowledge, that you have to remember these transforms, Laplace transforms of these functions. That will be very beneficial to compute several problems in future. So this is the end of this class, and we will discuss the rest part of this chapter in some other classes. So you need to just practice this in your own, and then everything will be clear to you.